Dilution of a solution. A very common way of making solutions in the lab is to take a more concentrated solution called a stock solution and diluting it. We call it a stock solution and we keep it in the stock room, right? It's in stock. So we've got that on the shelf. And it's more concentrated, most likely, than anything we're going to use. But that's nice because then we can make whatever concentration we need. We don't have to have lots of different concentrations available. Just the one concentrated solution, and then we dilute it. We do this with orange juice, too. You go to the grocery store, and you can buy, a big gallon jug of orange juice, or you can buy a little can of frozen orange juice concentrate. There's advantages to the concentrated solution. It takes up a lot less space in your freezer. Could you freeze gallon jugs of orange juice? If you were careful, you could. But those suckers would take a long time to thaw out, wouldn't they? And they'd be really heavy to transport, blah, 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 lots of problems. So they concentrate it. What do you do with that when you want to drink the orange juice? You squish it all into a big pitcher and you add water, right? So compare the little can and your pitcher of orange juice. Which one has more orange goodness in it? Well, the jug has more water in it, but the amount of orange stuff is the same, right? Because it came from the little can. Hopefully we didn't lose any if you do it carefully. You don't lose any when you dilute the orange juice, but you don't gain any either. All you're doing is increasing the volume. You're adding water, you're changing the concentration, but the amount of solute is the same. Does that make sense? Orange stuff doesn't appear and disappear out of nowhere. There's conservation of orange stuff. Okay? So the same thing happens when we dilute a solution. The amount of solute doesn't change. The amount of solvent increases, the volume of the solution increases, and the concentration, the molarity, decreases. But the solute, the stuff, stays the same. So there are two different approaches to solving dilution problems. One's conceptual and one uses algebra. So we're going to do the conceptual approach first. So we're going to pretend we're working in the chemistry stockroom. And the boss says, I need you to make 2 liters of 0.3 molar KOH from this 5 molar stock solution. Go. Oh, what do we do? We just start adding water? Well, it must be like orange juice. We'll just take this can. No, we're gonna figure out what's going on here, right? So the basic idea here is the amount of solute doesn't change. Well, how much solute do we need to have 2 liters of 0.3 moles per liter KOH? Could we figure out how many moles of KOH there are? Yes, we could. So this 0.3 means 0.3 moles of KOH per liter of solution. And how many liters do we want? 2 liters. So 2 liters times moles of KOH per liter, that's 0.3. That will give us 0.6 moles of KOH. Does that make sense? In the solution that the boss wants, there will be 0.6 moles of KOH in that 2-liter volume. So what we need to do is we need to figure out what volume of this solution is going to contain 0.6 moles of solute. We'll put that in the big container and we'll add water until we get the right volume. So we want this many moles of KOH. This is also a conversion factor, a unit factor. It's 5 moles of KOH per liter. So I can do another calculation down here. 0.6 moles of KOH. I want to know the volume of this other solution. I have moles here. I want volume. I'm going to put liters in here. Liters, and then moles of KOH go on the bottom. So those cancel out. 5 moles per liter, 5 moles per 1 liter. 0.6 divided by 5, 0.12 liters. So to prepare 2 liters of 0.3 molar potassium hydroxide, I'm going to need to measure out 0.12 liters of the concentrated 5 molar solution and dilute it, add water until I get this volume. Does that make sense? It's just like making orange juice from concentrate. So don't drink potassium hydroxide. It's not good for you. So that's the conceptual approach. There's another approach using algebra. So here we have an equation. M1V1 equals M2V2. We're going to do the same problem. Some books will show this MCVC equals MDVD, D and C for dilute and concentrated, but it really doesn't matter. So the 1 and the 2 is actually better. When you look at this problem, you're going to have, you're going to be given 3 of these 4 numbers and asked to find the other. So this is a volume, this is a concentration, a molarity, and this is a molarity. We need to find out another volume. This volume goes with this concentration. We can call these 1 or 2, but they go together, so they need to have the same number. Since they came first in the problem, I'm going to call them 1. So I'm going to say that V1 is 2 liters, and M1 is 0.3 moles per liter. And then this is a molarity. It's the other one, and so that's going to be M2. M2 is 5 moles per liter. So what am I trying to find then? I'm trying to find V2. So I'm trying to find this guy. So I need to use algebra. I need to rearrange. So I'm going to divide by M2 on both sides. So V2 equals M1 V1 over M2. I already identified all of those guys. So M1 is 0.3 moles per liter. Leave the units in there. Always use your units. V1 is 2.0 liters. It's a decimal point. And then I'm dividing by M2, which is 5 moles per liter. Everybody okay? What happens to those units? The moles and the moles cancel, the liters and the liters cancel. So I'm left with a volume unit, which is good because I'm finding a volume. 0.3 times 2 divided by 5 equals, V2 is 0.12 liters. And I heard several comments, that's way easier. Yeah, for some people, the algebra way is much easier. And for other people, the conceptual way is much easier. So use the method that works for you. Any questions? An example. Battery acid is 18 molar sulfuric acid. What volume of battery acid must be diluted with distilled water to prepare 1 liter of 0.5 molar sulfuric acid? You want to do conceptual or algebra? Algebra. The algebra people are vocal. We'll do algebra. Okay, so 1 liter and 0.5 molar go together, right? It's this volume of that one. And then we've got this guy out here by himself. So I'm going to call the first one M1. So that's 18 moles per liter. And then 1 liter, and I've got 0.50 moles per liter. So this is an M, and this is a V. I'm going to call them 2. If you call them 1, that's fine. You'll be solving for V2 instead of V1. It doesn't really matter. So M1 V1 equals M2 V2. I need to find V1 this time, right? Because I've got M1, but I don't have V1. So I'm going to divide by M1 on both sides. Those cancel out. So V1 equals M2 V2 over M1. Those are capital M's. M2 V2 always makes me want to say R2D2. Molarity 2 is 0.50 moles per liter. Volume 2 is 1 liter. Divide by molarity 1, 18 moles per liter. Again, these units cancel out. We're left with the volume. 0.5 times 1 divided by 18. .0.02777 forever. That'll round up to 8. 18 molar has 2 significant figures. 0.50 molar has 2, and so I need to round this to 2 significant figures. That's the volume in liters that I need to make that diluted solution. Any questions? A common mistake is to get something exchanged or backwards, and so you might end up saying that you need 2.8 liters of the 18 molar solution to make 1 liter of the 0.5. Could I put 2.8 liters in 1 liter? No. So in these sorts of problems, you can usually look at this number and see, is it reasonable? It can still be wrong and be reasonable, but at least you can catch the ones that are unreasonable and obviously wrong.